Alright, so for this first problem here, we have students standing on top of a building with two balls here, A and B, and the student's going to throw one ball straight up in the air. That's going to be ball A with an initial velocity that we're going to call V0, the velocity at time 0, and he's going to throw ball B also with an initial velocity of V0, but it's going to be straight down like that. And we're asked which ball hits the ground with a greater speed. So what I would think about when you're thinking about this problem is some of your free fall concepts, specifically the fact that when an object is thrown up in the air and it returns to the spot where it was thrown from, whatever speed it had going up is going to have the same speed going down, just the negative of that initial speed. And so what we can think about is this ball A here, when it goes up, it's going to travel up, reach some peak, and it's going to return, okay, to this same spot here, traveling with the same speed but going down. And so it's basically going to be identical to B, which means that both balls will hit the ground at the same time. So we want to justify our selection qualitatively without using any equations here. So we're basically going to say what we just talked about using those free fall concepts. So to start off my explanation, I would just say that when ball A returns to its initial height after reaching the peak, it's traveling down at that speed of 0. And from there we can just say that since it's now identical to the initial velocity of ball B and they both accelerate down at the same rate, and that is a key component of this, that they're both accelerating downward at 9.8 meters per second squared, they will reach the ground traveling at the same speed. Alright, for this last part, we want to go ahead and derive an expression for the velocity when hitting the ground, so we're going to set up our kinematics. It doesn't really matter which one you pick because we've already shown that they'll be traveling at the same speed when they hit the ground, but I'm just going to set this up for A. So I know that for A, my displacement is going to be negative h, where h is this height here of the building, negative of course because we're losing height. My initial velocity is going to be v0, and my acceleration is going to be negative g. Since I'm solving for final velocity, the best equation to use is going to be that vf squared equation, so I can go ahead and set that up. So I find that my final velocity squared is equal to that v0 squared plus 2 times negative g times negative h. So I find that the final velocity squared is going to be the square root of v0 squared plus 2gh. The two negatives, of course, make a positive. Now when we do that square root of vf squared, which we did in this step right here, we are left with plus or minus, and based on the sign convention I used, it should be negative, although probably if this was an actual AP problem, they would say magnitude, and then you would just take the positive either way. Alright, for this next problem here, we have a rocket being launched from the top of a roof. It's going to accelerate upwards for some period of time here up to t. Due to the engine. The engine's then going to burn out. It, of course, is going to continue up and eventually fall back down and land on the ground below. Okay, so the first thing we want to do is we want to sketch the velocity versus time graph that shows this motion. So initially we're going to have a positive acceleration and we're going to be speeding up for some period of time here. That's up to that period of time that we are calling t. All right, and then after t, which is right about here, okay, we are going to be slowing down at first, okay, accelerating at negative 9.8 meters per second squared, eventually going down, crossing that x-axis, and going down and having a negative velocity. Okay, so the basic sketch of the graph would look something like that. We do need to make sure that we actually cross the x-axis because this point here, where velocity is 0, is actually just up here at the peak. Okay, it then needs to have a negative velocity as it falls back down. The next question, or the second part of this, is we need to label that point, as I just mentioned, where it reaches its highest point, and that is going to be right here on this graph. That occurs when the velocity equals 0. That's when it changes directions and actually starts falling back down. So for this next question, it asks where the maximum speed achieved by the rocket is going to be greatest while traveling up or while traveling down. And the correct answer here is the maximum speed is going to be greater while traveling down. And we want to justify this in part C with specific features of the graph. So what I would think about here is that the maximum speed while traveling up, which is this blue portion, okay, that all represents our upward motion because we have a positive velocity. The maximum speed is achieved right here at that point, all right? And that's when the engine burns out and it begins to slow down, okay? When we're traveling back down, all right, we're going to reach a point, all right, at an equal height, and I'll say it's at a time here of t2, where our downward velocity is equivalent to the upward velocity we had at the same height. So whatever velocity we had here at t, we're going to have that same velocity here at t2, all right, because it returns to the same height. So t2 is going to be somewhere, all right, around here. And the reason we know that, we actually can think about the meaning of area. We know that the area of this little triangle here, that distance it travels going up to the peak, okay? And the area of this little triangle here, that distance it travels from the peak back down to this point, are equal, okay? So T2 is going to be somewhere around in here, all right? That's where we return to that spot, that height where our engine burnt out. And at that point in time, our downward velocity will be negative V max, okay? But we notice that this line then continues to go down, okay, as our rocket continues speeding up on the way down, and therefore right before it hits the ground it'll be traveling faster than it was traveling here, and that means that we achieve our maximum speed on the way down as opposed to on the way up. Alright, for this last problem here, we have two identical blocks, A and B, that are placed on a frictionless ramp up here. They're both released from rest. A slides down, slides through this dip, and up to this point here. When it's launched in the air, B slides down along this flat surface and is launched off into the air. So what I would think about with these two is which way they're launched. So A is launched up at an angle like that. Okay, B is just going to be launched horizontally, going out to the left like so. So the other thing that's going to be important here is to realize that they're both launched at the same velocity. Okay, they both start from the same height here. They both end up launching from the same height as well. Now I realize A drops down at this little dip, but when it actually launches, it's at the same height that B is when it launches off the table. And so from an energy perspective, they're traveling at the same speed overall when they launch. The only difference is that A, okay, is launched up at an angle, whereas B is launched completely horizontally. Keeping those two ideas in mind, we can start to answer part A here. And so we want to know which one will be traveling faster when it reaches its highest point after leaving the table, okay? And what I would think about is just your components, okay? We know that when an object reaches its highest point, it has no y velocity. So all we really care about are these x components of the velocity, which for the one launched at an angle, block A, that x component is less than the overall velocity. For block B, it only has x velocity. So the x velocity is going to be greater for B than it is for A, which means that the highest point, A, will be traveling slower. Next part of the question here asks which one will be traveling faster when they hit the ground. And once again, we're going to look to energy to help us answer this one. I realize this is in the kinematics unit, but it's sometimes tough to get away from energy and have ones that only focus on kinematics. And energy is an important thing that's going to come up a lot and is probably worth reviewing anyway. So what I would say for this one is basically the same argument we make. They both start at the same height above the ground. They both land on the ground, so the same amount of potential energy is converted to kinetic, and therefore they hit at the same speed. Last question here asks about time, which one will hit first. And for this one, you do need to draw upon some of your projectile motion concepts here. But really, there's only one thing you need to focus on, and that is this right here, the y component of the initial velocity for box A. Box A has a y component, box B does not. And so that means that box A will first travel up in the air and then fall to the ground, whereas B is just going to immediately fall to the ground, obviously traveling some horizontal distance, but from a vertical motion perspective, B is just going to go down, whereas A is going to go up and then fall down from that point. The y motion ultimately determines the time it takes to hit the ground. It has to fall a distance here of whatever the height of the table is. So that means that box B will hit the ground first, okay, because it doesn't have that y component of the velocity.